Yes, I'm Phil Day. I'm the Director of Engineering at Configured Things. We are a company that focus on configuration management in complex distributed environments. We've done a lot of work with the NCSC, and in fact, we're actually leading some alpha testing for DCMS on the connected places security principles. So why am I kind of here talking to you about configuration management in security? Well, misconfiguration is one of the major causes of security breaches, whether that's accidental misconfiguration or malicious, and configuration management systems and identity systems are becoming big targets for these things. So I'm going to talk about how we can mitigate some of those risks and how we can try to reduce the attack surface in the configuration management space. And I'd say there are kind of three broad areas around this. One of the first problems we have is complexity. Now, you keep hearing complexity probably from all the talks, and complexity is generally a bad thing when you want security. So the more complex an interface is, the harder it is to use, the bigger the chance that you're going to get misconfiguration. And also the harder it is to even tell if it's configured properly, because there are too many moving parts in there. The second problem is generalized interfaces. So if you look at most systems, they have a configuration management interface that exposes the full set of potential options for that system, and then they have a security model applied on top of that to try to constrain it down into domains. That means you're kind of only ever one misconfiguration away from opening up a capability you didn't want to some particular role. And the reality is there isn't a single source of change into these systems. The changes are coming from multiple places. And then finally, we need to look at resilience, right? It's not possible these days to make your system 100% secure. You have to think about, security guys are always looking on the bad side of these things. What am I going to do when something happens? Well, how am I going to recover quickly when there is a breach? And this becomes quite a difficult space in the configuration space. We're going to look at how we can approach these areas differently to do things with configuration. So I'm going to use a couple of examples to pull out the patterns. These are things we've been working on recently. The first is an innovation project, Innovate UK project called Synergia, with a mesh radio network and some AI actors in there. And the second one is one we've been working on with a local council, with NCSC. Again, they're looking particularly at the governance aspects of this, as well as the technology aspects of how to put together smart systems that are a lot more than just the network and are systems not owned by one people. And what we can see across these are a number of kind of characteristics that have driven the way we're trying to push the design now. We have systems that are out in untrusted locations, which means they're vulnerable to being compromised. And we've got to be able to work out how we can get these back into a good state. They are inherently distributed systems, which means we've got configuration that we need to propagate through the system to make sure the whole thing stays consistent. And we can't require that the network is always going to be there. So there's a risk of the configuration drift if something is offline when we're trying to make a configuration change. We've got automated sources of change. We've got AI systems as well as people trying to drive things in here. And we have overlapping roles. These don't define nicely into small subsystems that you can say that's completely controlled by this role. So when I look at these, we have a number of capabilities that we want to build out of the configuration interface. It needs to be simple, and it needs to be specialized to each role. We want it to be simple so that we can avoid misconfiguration, and also so that we can tell from inspection what state this is in and what's really being configured. And we want to specialize it because we want to constrain the attack surface and be really in control of the attack surface of the configuration space. It needs to be something that can be fully automated. And a lot of configuration systems are kind of based still on the assumption that you've got a static configuration file or you're driving something through a GUI, and that just doesn't work. If you're trying to build a system that's smart, it's got to be able to change. We have to be able to cope with overlapping roles. We have multiple actors in here, and they need to come together to collaborate across these systems. Equally important, there is a trust relationship to each of these roles, and we've got to work out what we're going to do when that trust relationship changes. It may be a technical breach, or it may be a social breach of some set of compromised credentials. We have to be able to react to that. And in the configuration space, normally when you think about it in networking and you hear about zero trust in networking, you can just say, okay, what connections do I drop? Who am I going to allow to reconnect? In configuration, it's not just about changing who I trust to give me new changes. I've got to work out how to get out the changes that are in the system now from the people that I no longer trust. I've got to be able to retrospectively apply the policy now. And then finally, these are distributed, right? We need to be able to work across distributed systems, and when we're looking at You know, one of the reasons NCSC are very interested in this is things are rapidly becoming things that drive critical national infrastructure. We've got to be able to work across trust boundaries and security boundaries. Now, interface complexity is kind of one of those major problems that drives this. Like I said, you know, REST interfaces, the things you'll typically see on a component, are complex and generalized. And one of the things that you can do that we've seen emerge a lot in the infrastructure as a service type space is to move to a declarative configuration approach. And declarative is really great. It moves the complexity from the interface into a controller. So you're basically giving a statement saying this is the outcome that I want. So declarative is good, and we've worked with declarative systems for a long time, and we build on that. But the general way that declarative is used in what you might hear of as the DevOps case, where you have people that are developing configuration in the same sort of life cycle that code does, has a few kind of restrictions for us, a few limitations compared to the use cases we want to get to. It's generally kind of based around non-overlapping roles. You tend to divide the system down into a number of stacks and work out who owns the declarative configuration for that particular stack. It tends to kind of follow, because of that, and expose the system architecture, which isn't what we want. We want to simplify the configuration management, so the things that are asking for outcomes are asking for it in terms that they understand, not trying to understand what my system does to expose it. These kind of controls also tend to only apply at the edge of the system. You're verifying the configuration as it comes in, and then you're acting on it. We want to be able to carry that concept of trust all the way through the system, so the systems we're feeding into can also see why they should be able to trust that change that's been asked for. And then finally, of course, as I said, with distributed, we need to automatically propagate these changes as they're going through into the system. So what we do in our declarative way is we look at it slightly differently. We manage, for each of the roles, each of the sources of configuration change, we manage a set of requests from each of those. And each of these inputs is a declarative statement. It's a desired outcome that that particular role wants from the system. And they're specialized to each of those roles. And for each of those, we have a trust relationship. Now, by specializing these, I can make it that a system that can tell me about devices can never accidentally tell me about gateways. It's not even in its language. It's much simpler to stop it for asking them for the wrong thing than to try to have access controls to do these things. So each of these is its own grammar. It's its own declarative statement in a role that in a space that it understands. And what we do is we take all of these and we merge them to form a declarative statement of the system or some part of the system. And what's important is we remerge these and reevaluate these whenever any of them change. So the thing we're managing isn't really this. This is a derivative from a set of requests that we're always managing. And we can also re-trigger that merge and reevaluate all of those requests when our trust relationship changes with something. So if we no longer trust one of the actors in role 1, we can reevaluate all of these against a new security policy and apply only the changes that are now valid and produce the new declarative version, which we then pass on to the controllers to bring the system into compliance with that view of the world. So we're doing two things here, really. We're trying to mitigate the misconfiguration by simplicity on the interfaces, making them declarative, so they're stateless from the person that's supplying stuff to us, and from specializing them out to each role. And we're providing the resilience by treating all of those things as ephemeral, so that we can always go back, if you like, to first principles of the outcomes that are currently asked for from all of the roles and apply them against the current policy to understand where we are with things. Now, that's great. We've got declarative statements coming in. We've got a nice, simple interface, but we have to be able to trust it. So how do we put trust back onto this system? Well, we, like everyone, we really believe in the zero trust approach for these things. Zero trust, never trust, always authenticate. You quite often hear it, applied at the network level. Don't trust this system just because it's on this particular subnet. Don't trust it because you know who it is. In our case, zero trust means each individual request is the thing we want to authenticate and authorize. Now, the nice thing with being declarative is we have structured data, and you can think of that structured data as a document. And the thing about documents and structured data is you can digitally sign them. So we sign the change requests, or we insist that they are signed by the source. And that gives us both, who the origin is from these things, and also tells us that this is consistent because the signature is based on the contents of those. So it doesn't matter to us where these have come from or how they got to us. They can be in clear text in the transport if they need to be. They can be over an encrypted channel. But we know it's unchanged and we know where it's come from. And then our trust policy can be based around the signatures that we have on here. And we can carry multiple signatures on a request if we need to. So in the cases where we're really controlling something that you would consider CNI and we want to protect against a lone actor, a lone compromised set of credentials, we can have policies that say, well, there must be at least 2 signatures from this group, or 1 signature from this group and 1 signature for another group. And we can carry that concept of trust all the way through where we've got these declarative statements and re-sign them as we want to. So we have an inherent protection here at the level of each change request, which, if you like, are our kind of atomic units for rebuilding what the state of the system should be, that is carrying all the information it needs for us to be able to re-authenticate it and reauthorize it. Now, when you build the system this way, and the important thing, as I said, is we're going to, if any of the trust changes, we're going to reevaluate all of these, and it's easy then to filter out the ones that are no longer trusted, the ones that were no longer signed by Alice. If it's still got enough valid signatures on it, we're good. It's good in the system. If it doesn't, that change should have never been put into the system. We're not trying to roll back to some previous state and trying to work out what do I have to undo to get back there. We're just asserting what's the new set of outcomes that are actually valid at this point in time and then building the configuration from that point. So when you build the systems this way, and it's kind of hard until you've actually tried to use a system like this, there are some really nice operational properties that come out of this. There's complexity you have to build for the controllers, for sure, but operationally, so each role is just always telling us what outcome it wants now. And it's telling us about an outcome. It's a declarative statement in a grammar that's specific to it that says, this is what I want. That's inspectable by anybody that wants to see what the outcomes are that are being asked for. Removing a change, if a role no longer needs that outcome for some reason, is as simple as just taking it away from the system. There's no undo. That role doesn't have to look at the system and think, who else has made a change that might have affected this? What have I got to unwind, right? And anybody that's worked in configuration management or programming will know that handling all the exceptions is the hard bit, not designing for the happy case when everything goes through. We don't have a concept of undo. You just take the request away. When you take the request away, reevaluate everything else that's there. We have no race conditions or state issues between overlapping roles. If I've got 2 roles that are configuring separate things, and taking your case maybe from the drones, there's a requirement to have something from the aviation authority and a requirement to have a flight plan from somewhere else, I don't mind which order those come into, because whenever one of them changes, I'm going to reevaluate everything. If there are dependencies between them, I can handle that in the system. So a request that depends on something else is still valid from that role, but it won't get merged into the system until its dependencies are met. Equally, if those dependencies are dropped for some reason, that request is currently no longer valid or no longer processed. It's still valid, it's still a statement that that role wants that outcome, but it's not actually being applied to the system. So the system appears stateless and idempotent across all of those inputs, which makes the system a lot more predictable and a lot more resilient than having lots of other systems trying to worry about the state and how to recover things. What's nice here too is that we get a common interface pattern across the systems. We're taking declarative statements in explaining an outcome. We're merging them to form an overall declarative statement of one system or multiple systems. I've talked about this as one system, but in reality, each of our systems can be working like this. From that new declarative state, we can derive new submodels that we can sign and pass on to the other systems. So all of our systems are interacting on this basis of being given requests that come through. Because of this, we're not really just considering trust at the edge. It's not just a question of, have I got my web server secured? Is my REST API secured? Changes now in the system and propagating wherever. We can carry signatures through into the model, and we can see who signed this block of data, providing it's been unchanged. If we have to remerge it, we can sign it with something that represents that part of the system, that certifies it was signed there. So anything that receives a sort of an artifact from this request from us can itself verify where that has come from. So trust is inherent all the way through, not just an edge property. And equally, of course, Because our systems are working, they can always rebuild what state they should be in. They can disconnect and then they can come back, and we don't have this same issue of configuration drift. A system can start from a good, safe base state, and then it can rebuild its configuration to what it needs to be, even if that's changed while it was offline, which is really important when we've got these systems that are out in the untrusted space. Now, as well as sending state and configuration in, we do have to get data back out. So every role, every interface, we give a status interface to. But this is completely asynchronous, because bear in mind, the validity of a request can change at any time. It's not a question of was this accepted once, it's is it still valid in the system. So the status that we report back is a structured data that is sent every time there's a change inside the system. And inside that, as well as the status of the request, was this valid, was it syntactically correct, etc., has it met its dependencies, we can provide a role-specific view of the system. And we can see what we're sending back out to each system. We're not exposing a state API, so we can prevent data leakage. We can be really sure who's seeing which part of the system and what information is being shared. All of this is about being transparent and inspectable at that edge. Now, building a status view from lots of different sources and recalculating it every time something changes is a fairly complicated task. But luckily, we have a system that is really good at taking structured data and merging it together to form an output. And that's effectively what we do. We kind of run that configuration pipeline, that merge pipeline in reverse. We can pull status from wherever, and we can create our structured data saying what the state is. And it's structured data. We can sign it as we send it back to the system, so the system can be sure that what it's getting from us is signed and can go back over an untrusted channel if need be to do things. One of the things that gets really important with this, when you start to work into the industrial space or you're working with CNI, is how am I going to work across a security boundary? Now, in our case, this fits really quite nicely. We have, these slides have gone a bit weird, but imagine these are actually the signatures on the documents. We've actually got a very simple set of data we're sending in each case, which can be inspected. So you can tell what this data is, whether it applies to the right schema, make sure it hasn't been corrupted on the way through. The requests and the status are fully asynchronous and they're independent. So we don't need a bidirectional transport here. In fact, we don't even need a concept of session across here. Everything we're carrying is included within this declarative block, this document that we're able to cross across the boundary. So it actually makes it easy to work across things even if you have a concept like a pair of data diodes in here. We're not trying to expose REST calls or sessions or any of those sort of things across the boundary. So in summary then, the way we're trying to approach this to reduce the risk of misconfiguration, to get the attack surface down, to provide the simplicity in here is, we're taking a declarative approach which reduces the complexity. It reduces the complexity in terms of what things need to ask for, because they can talk about the outcomes they want. They don't have to know about the system. And getting rid of complexity reduces the risk of misconfiguration. Having a role-specific interface also reduces the risk of malicious misconfiguration. Because, as I said, we just don't give roles the language to express anything more than they need to. We use zero trust. We've got the signatures on here. That gives us this ability to not trust the transport or the origin, but we just trust each request in its entirety. We can mitigate against insider threats because we can carry multiple signatures, which really isn't something you can do if you're trying to drive something through a REST interface or a GUI. And we can allow that concept of trust to extend beyond the interface because we can carry the authentication of something with the data that goes with it. In fact, in the model, we can even introduce new constraints that says only allow something to change here if it carries this set of signatures. So we build all of those things up and we try to keep everything constrained rather than having a separate system. Always contained, always inspectable. And then finally, the important thing that makes us different from other declarative kind of DevOps way is we're re-evaluating these on any change. So each role can see our system as being completely dateless. It just has to think about what it now wants. The roles can overlap in scope, and it doesn't matter. There's no timing issues between them or shared state issues between them. And being able to do this and being able to change on request is the thing that gives us this resilience to changes in trust. We're not just making policy about what can happen from here. We're making sure the policy we've got is always consistent with where we are. Thank you, and hopefully I'm just about there.
Absolutely spot on to the minute, actually.